All right, yeah, we have our third talk in this session on an important topic, I think across, computer science, machine learning, and other topics, but also for profits. So please, Makis, sorry.
Hi everyone, I'm Makis. This is joint work with my advisor, Kleinberg, who's in the audience. And before I dive into the profit inequalities part, let me talk to you a little bit about fairness. So we design algorithms, and especially in the economics and computation community, those algorithms make decisions that affect real people. So it's very important to handle those, to make these decisions be fair to individuals, okay? So how do we define fairness? It's a difficult question, and there have been many approaches to it over the years. So one particular type of fairness is individual fairness, which is the general notion that similar individuals should be treated similarly. And as a side note, you might be familiar already with another type of fairness, which is group fairness, and there has been work that connects group fairness with profit inequalities, but we will not touch upon it much at all in this talk. Okay, so what I want to do is to give you examples that define, to give you an idea of what kind of fairness we want to talk about, and then I will dive into the more technical stuff for profit inequalities. Okay, so my first example. So I want to focus on two types of individual fairness. So example number one, which will showcase this one type of fairness, is suppose you are in a small town and there is a ride-sharing application like Uber or Lyft, and suppose there is only one rider available at any time and two potential customers. So the customer on the right is a frequent traveler, meaning that they request a ride almost every day. They use a ride everywhere they go. The person on the left, on the other hand, they mostly use public transport, except today they missed their bus while going back from grocery shopping, and they live far away, so they have to get, let's say, an Uber. So suppose that they both get on the app at the same time, and since there is only one ride available, let's say the app randomizes and flips a fair coin to choose between the two who gets the ride for that day. Okay? So you might think that this is as fair as it gets because the coin the app flips is fair. But there is a sense in which this is not. And to show that is, suppose that these two people later meet and they discuss their experience from using ride-sharing apps in this town. So the person on the right would be much more satisfied because most of the time they want a ride and they actually have it. There is no competition. But the person on the left, the very few times that they actually want a ride, half of the time they don't get it because they're blocked by the other person who most likely would request a ride. Okay, so this is a kind of contrived example, but I hope it drives home the how the algorithm treats the two people who are otherwise similar. They both request a ride. It treats them on average not similarly. Okay. Second example, which might be more familiar to you, is the process of applying for grants. So usually there is a specific deadline by which all applications come in, and then a decision is made when all of the applications can be evaluated. But suppose now that we're in a case where there is no deadline, but applications come in and they are evaluated on the spot. Okay? But there is still, and in fact NSF does this for some kind of projects they're funding. But there is still a budget. Maybe every fiscal year. So the time at which you apply, it matters for whether you get the fund or not. Or rather, there can be things that go wrong if you don't make the decisions correctly in such a scenario. So one thing that can go wrong, there might be many, but one thing that can go wrong and make things unfair is, suppose you have two projects. They are both equal in the sense that they will have the same contribution to science, but the two people applying for grants for those projects, one of them applies early, the other late. And let's say that the person who applied early was rejected because they were on the borderline of satisfying the criteria of the grant. Okay, but later on, the other person applies towards the end of the fiscal year. So at that point, there is a lot of leftover budget. So instead of burning it, and since the project is on the borderline, They allocate the funds to them. So this is one unfair situation that can arrive because you didn't have a specific deadline. OK, now keep in mind those two examples, and we will come back to those. I want to apply these two notions of fairness. Those two notions that I described are slightly different. And I want to apply them in certain online and offline decision-making problems. OK, so in particular, profit inequalities, which we'll introduce really briefly. You've seen some in the previous talks. So you have n independent random variables where we know their distribution. And you can think of this, if you've never seen profit inequality problems before, as the xi being the fitness of a person for a particular job. And you want to hire one person out of the n people, but you don't know how good they are, so you start interviewing them in order. And the catch is that you have to make a decision immediately. You cannot just interview all of them and then go back to choose the best one. So your goal is to maximize on expectation the value of the person you pick. OK? And this is the standard profit inequality. It was explained in previous sessions, but let me just briefly go through. So it says that for any particular instance, the optimal online algorithm that chooses one of those variables gets on expectation at least half of what a prophet would get, where the prophet is someone who knows all the variables. Okay? And now, as was pointed out before, this is both for the optimal algorithm. And what do you mean by optimal algorithm? This is the algorithm you will get if you, for this particular instance, do a backward induction argument. And basically, you will come up with a sequence of thresholds, T1 through Tn. And when you're trying to make a decision whether to hire the ith variable, you just check if it is above the threshold or not. Okay? But there are also much simpler policies that achieve the same competitive ratio. For example, setting a single threshold. So you use the same threshold for every variable to make your decision, which could be set by this function, for example. So how does the unfairness that I described before, how does it appear here in profit inequalities? So one is discrimination on arrival time. So think of the NSF example, the funding example. In the context of profit inequalities, if you're using a uniform threshold algorithm, then a person who arrives earlier, they have a higher chance of being the one accepted because they face less competition. But this can also happen in reverse, sort of mirroring the example I said before, if you use like decreasing thresholds. So a person that has a relatively low value, they might want to actually arrive late so that they are compared against a lower threshold. Okay? So this is some. So these algorithms, the classic algorithm for profit inequalities, are fundamentally unfair. And so what we want to do is to try to fix that by imposing fairness constraints. Okay, so that was the first type of unfairness. And so here's how we fix it. So we impose another constraint, which we call time-independent fairness, that corresponds to the funding example I took before. In order to be able to define that, I first need to slightly augment my model to be able to talk about arrival ordering, because in standard profit inequalities, the order in which people arrive is fixed. So I will add a superscript to my algorithm, which is a permutation pi, that indicates that the algorithm has to inspect the variables in the order x of pi 1 up to x of pi n. And so if you give me a family of algorithms, one algorithm for every possible permutation that the people can arrive, then I can tell you if this algorithm is fair or not by checking the following condition. I would just look at the probability of the algorithm hiring a particular person I, conditional on their value being some value x. So this is looking at it from the perspective of the ith person who knows their value. And I check if this probability is independent of pi, the arrival ordering. If it is, then it is fair according to what I described before. You do not see any unfairness like the example, the funding example. Okay? Now, let's go to the other type of unfairness. Think about the Uber example again. And here's how it appears in profit inequality. So if you have two random variables, one of them is most probably 1, the other one is most probably 0, and you run an online algorithm with a single threshold, then if you compute those conditional probabilities of the algorithm hiring its person, given their value, so we're fixing the value, looking at it from the perspective of that item on a sort of interim point, we see that those values are vastly different. One is getting hired with almost 100%, the other one almost 0. And that's actually not an artifact of the online nature necessarily. It also happens in an offline setting where imagine you are the prophet, you know all the realizations of the values, and let's say, so I have to specify what you do if you see both of them being 1, and let's say you flip a fair coin to decide between the two. Now, if you compute, again, the same conditional probabilities, you'll see that the person 1 has a much higher probability of getting hired compared to person 2, given that they have the high value. And this is because of the competition they each face. Think, again, about the Uber example before. OK, so the property that we want in order to avoid this bad situation, we call it identity-independent fairness. And it's similar to before. Now, we don't talk about orderings. It's like a fixed ordering, again. So if you give me a single algorithm, I can tell if this is fair according to this definition. If I compute the probability of hiring that person conditional on their value, if that is independent of I, then it is fair. So that means that I don't care who you are in particular. I hire you based with odds based on your value, actually, not your identity. OK, so what is the plan for the next few remaining minutes? We need to solve the profit inequality problem optimally under the IIF constraint or under the TIF constraint. That will be one goal. And the second one is to prove profit inequalities. But now the landscape is more interesting because before we had the profit on the one hand and the online algorithm on the other. Now adding fairness adds another dimension to the problem. So we can compare, for example, an offline but fair profit with an online fair algorithm, or online with online fair, and so on. And the goal is to fill up those arrows with competitive ratios comparing those settings. OK? The one half that I have there is the standard profit inequality. OK, so for identity-independent fairness, our approach for solving for the optimal algorithm, in contrast with standard profit inequalities where the solution is a backwards induction, so a dynamic program, here we have a linear program where the variables are p of x, where x is a support point on the, of the distributions. So you have one variable p of x for every support point, which should be interpreted as the probability of hiring a person given that they have this value x. And because of the IIF constraint, there is no dependence on I here, so I can just call it p of x. The objective is just the expectation of the algorithm expressed in linear terms with using the variables and the distributions fi of x of the random variables. And the constraint is basically saying that because not all possible vectors of probabilities correspond to actual algorithms making decisions, we have to make sure that those probabilities can be translated back to an algorithm. And it turns out that the necessary and sufficient condition for that is the inequality that I have there, which basically says that the probability of hiring a person, given that they have a value x, should be bounded by the probability of reaching that person. Or it's enough to say that it's bounded by the, it's enough to require that only for the last person, actually. So once someone solves this LP, then all you have to do is plug the solution you get back into this algorithm. And how does this algorithm work? So you first inspect the first person, x1. What does the LP says? That you have to hire them with probability, and let's say, so their value is x, so you have to hire them with probability p of x. So that's exactly what you do. You flip a biased coin with probability p of x, and you hire them if it comes heads. Now, basically, this is what you want to do on the next few steps as well, but you just have to make sure you normalize by this value that I call q of I, which is basically the probability of having reached that step where you're interviewing the ith person. And so now the important takeaway from this is what does the algorithm look like? It doesn't have thresholds anymore. It takes the value, it observes the value, and then based on the value, it flips an biased coin of whether to hire someone or not. And this, in the end, will end up being a fair algorithm according to the IIF definition. Now, before I talk about TIF, so without going into the details of the proof, we prove a 1/2 competitive ratio between the hard direction, completely unconstrained profit, and an online and fair algorithm. So we prove that if you run, there is an algorithm, for example, the optimal algorithm, that will perform at least half as good as the profit and will be fair. This automatically gives us all these three results that the ratio is at least 1/2. And we, in fact, prove tight examples. So it is exactly half, except for the left edge, which we do not know, actually, if it is tight. Time-independent fairness is similar. We prove a similar 1/2 ratio with a similar LP. And everything is tight here. And in fact, we come up with an algorithm that it may not be the instance optimal, but it is a half competitive and is both TIF and IIF fair. So this is a summary of the competitive ratio results. And really quickly, what is the catch? So I managed to get 1/2 competitive and I get fairness, but there is something I'm missing here. So the thing is that all the algorithms I presented, like the IIF and the similar one for TIF, are randomized, and they have non-zero probability of hiring no one, which was not a problem in standard setting because you could always hire the last person you see. But now if you do that, you're no longer fair. Like the last person will have way more probability of getting hired. So you cannot do that. And in fact, what we prove is that it's impossible to have any non-zero competitive ratio if you want your algorithm to hire with probability 1. Okay, and I'm not sure if I have time, 2 minutes. Okay, so really quickly, the last setting we consider is what if we don't know the exact distributions Fi that the variables follow, which you might think it's hard to solve because now we don't have those probabilities to plug into the LP. But turns out we can do good enough by having access to samples of the distributions, which corresponds to knowing past observations in real world. Okay, so let me quickly just point out the theorems. We have an algorithm that works with it needs a single sample for every variable, and it's an offline algorithm, not an online one. So it is a profit. It sees all the values. It doesn't know anything about their distribution, but it also sees a sequence of samples. And it manages to be 1/2 competitive compared to a profit who is not constrained to be fair. That's for IIF. And in the online setting, we have an algorithm that requires 2 samples from every distribution that manages to be IIF and TIF and is 1/9 competitive. And we don't know if this 1/9 can be improved. That's an open question. Okay, I'm going to skip the summary and just leave it for questions, actually. Thank you. Yes?
Sorry, I have 2 questions. So I'm a little confused about the difference between the 2 definitions of fairness. Isn't your name and identity just your position in the order? Is one of these stronger than the other?
No, they're orthogonal in a sense. So one talks about, they correspond to the 2 examples with the Uber and the grant funding. They are fundamentally different kinds of fairness. You can have examples of algorithms that satisfy one of them but not the other.
But isn't your identity your position in the order, so you're kind of talking about?
Identity is the distribution from which your value is drawn.
Oh, I see.
Yeah.
Second question, so you're assuming in the time-dependent fairness, you're assuming that the algorithm is given the order. Is it obvious that it's impossible if, say, the order is also revealed online? Is it obvious that it's impossible to get fairness? It seems like it should be that, I guess, I'm not sure.
Let me see, I understand what you mean. So do you mean that I as an algorithm, do not know what is about to...
No, the order that you kind of learned as elements arrive, right?
I see. So then...
So these like strong adversarial order models.
I think this is stronger in a sense, right? Because this says it works for any family of algorithms that do whatever they want for its permutation. So those algorithms for its permutation, they could be completely different, and still it could be like TIF.
So I don't know if you probably can't solve your LP if you don't know the order up front.
Yeah, that's a good point. Yeah, so I will say that I'm not sure how to do that then, yeah.
All right. Yeah. I think in the interest of time, we also have to get to the next talk. I'm sure Makis is happy to answer questions. So thanks for this very nice result. And if you're interested, yeah.